where people have sort of used robots to do these inspections.
These sensors will be very quickly able to tell you.
So very interesting that we left it for curing.
Good evening and welcome everyone. With great pleasure and enthusiasm, we, the CES Club of NIT Rourkela, in collaboration with ICE UK NIT Rourkela chapter, bring to you an enlightening session of CIVINAR. This is Abhishek and I'll be your host for today's session of a very informative and encouraging CIVINAR series. Our previous sessions were graced by some eminent personalities from different fields of civil engineering for highly institutional webinars. To name a few, Professor Sriram Narasimhan from University of Waterloo, Canada, Professor Nemi Bhantia from University of British Columbia, Professor Rajshekhar Balasubramaniam from National University of Singapore, who gave their insightful talks to our student community. And today, we feel it as a great opportunity and fortune that we are joined by Professor Brij Kishor Pandey for this seventh session of CIVINAR. Before we begin our webinar, I would like to request Professor Subhajit Mandal, Assistant Professor from the Department of Civil Engineering of NIT Rourkela and the Chief Patron of CIVINAR Organizing Committee, to say a few words on today's auspicious event that we are about to witness. Professor Mandal.
Thank you very much to give me the opportunity. Actually, this CEST club of CIVINAR was started last year, and that time Satyadeep and other students, they worked very hard to start it. Now it's become a continuous process. I congratulate all the students, and I also welcome Professor Brij Kishor Pandey to start his talk.
Thank you, sir, for your encouraging words and guidance we have from you. Let me introduce our today's speaker to the audience, Dr. Brij. Dr. Brij is an assistant professor in the Department of Civil Engineering in Birla Institute of Technology and Science, Pilani, Dubai campus. He received the doctorate in water resource engineering development from the Institute of Technology, Roorkee. His research interest mainly involves around climate change impact and research and projection studies, hydrological modeling, flood forecast, GIS, and remote sensing. He has secured an All India third rank in recruitment of assistant professors in civil engineering through NPIU-TEQIP III, Project 2017 of MHRD and World Bank. For his excellent work in the field of civil engineering, he has been awarded with Young Scientist Fellowship and International Travel Support and the Netherlands Fellowship Program. Today, he will be delivering his lecture on the topic Introduction to Hydrological Modeling and Climate Change Impact Studies. Just a little housekeeping for our audience. Before we get started, if you have any queries during the webinar, do type them in the live comment section, as there will be a Q&A session followed by this webinar. Now, without any further ado, I would like to call upon Professor Brij to begin with his presentation.
Thank you, Dr. Mandal, for inviting me to share my research. And I'm very delighted and honored to be a part of this webinar of Rourkela. And also appreciate I'll much appreciate the effort of Abhishek, Satyadeep, Shubham, and whole organizing committee of this seminar to conduct this seminar at Rourkela. So I won't take much time, and I'll share my screen. So, Abhishek, can you see my screen? Abhishek, can you see
Yes,
my
sir,
screen?
it's visible. Yes, sir.
Okay, so just wait. Yeah. Okay, so thank you. So today, in today's talk, actually, I'll talk about hydrological modeling. It's a basic concept of the hydrological modeling and how it's associated with the climate change impact studies. So that we are going to talk about. So let me share some headlines of the news which is related to the water-related disasters which happened in India in the recent past. So in 2015, we might be heard about this Chennai flood that we had which has been declared as the worst, basically flood of the century. Apart from that, uh, we have already got the news about this Kedarnath tragedy in 2013. In that, more than 6,000 people were died, and there was an economy loss of more than 6.8 billions of US dollars, and more than that, there was a Kerala flood in 2000, basically 18. It's like just a couple of years before. So basically, these are the basically natural disasters happened in the recent past, and that basically indicates that, and that basically indicates the signal of the climate change. So this basically extreme precipitation and these floods are basically natural hazard which affect the human society as well as the economic loss. And this effect of this climate change basically it's basically increasing or amplifying the severity of this flood. So these floods are not limited to a certain cities or certain areas, but it's affects most of the states of the India. If I'll consider last couple of decades, the data from the last couple of decades, having more than or about 300 total deaths in this flood, so I found that most of the states like Uttarakhand, Bihar, Meghalaya, Maharashtra, Odisha, so almost it's like most of the basically states are affected by this natural disasters. And it is not restricted or limited to India only, but will go further across the world. We'll find that USA actually have received more than 200 number of flooding events during 98 to 2008. And in China is also received about during this 10 years of the period, China has also received about 200 of the flooding events. India is also not much far actually. It's received 126 number of flooding events. But if you see the total basically death in this flood disaster, we found that about 43,000 people were died during this in the last decade, whereas China and Venezuela is also having the about 30,000 numbers. So this basically these problems and this disaster, it's not only up to the particular country or particular. It's basically it's happening. It's affected. The people are affected across the world. So one of the basically study indicates, and this study is carried out by Tokyo Hoshio, chief researcher ICHAM Japan. Is consider some criteria of the disaster, such as 10 people or more people reported killed, 100 people or more people reported affected, declaration of a state of emergency, call of international assistance. So considering this disaster definition, he found that in the last 35 years of the span, within the Asia, this hydrometeorological hazard has been increased by 45%. Whereas in this world, whereas across the world, it has been increased by 86%, and as natural hazard also. So basically, it's indicating in the couple of decades this natural hazard severity and severity of this natural hazard has been increased by many folds. So If I'll do consider this natural hazard and affected people, we found that about 95.5% people are affected just by this natural hazard. Means either it could be a flood, or could be a drought, or could be a storm. So such kind of basically hazard it's affected most. So if I consider this climate change, if I consider fluctuation margin due to climate change, then we can consider the variability at this moment. It may be, we can see this projection of the variability of this basically climate change in terms of external force of this disaster that basically affect those natural disaster. We can see the fluctuation may be an average value at the end of the 21st century. So this phenomena basically, actually this alarming phenomena basically it's indicate the average or expected to occur 100 years from now may occur much sooner. Maybe this variability, this is basically a external force of disaster, it may be a average after the 100 years. So there are some phenomena basically we'll have to consider. So this climate change is severely affecting on the water resources and amplifying this risk and problems by many times. So it's not only affect the flood and drought, but also it affect the water supply shortage and distribution. Apart from that, also include this water quality and disrupted watershed process and so on. So what are the signals of the climate change basically that affects this hydrological cycle or hydrological chain? So as reported said, this climate change basically intensifying this hydrological cycle, and the end result we get the change in intensity and frequency of precipitation, and the glacier also reduced, groundwater also depleted, and the water in streams and lakes become warmer, sea level basically rises, and due to temperature change there will be some change in evapotranspiration, dried vegetation and soil, and more frequent basically severe drought we occurred. So more than that, so more intense storm with more flooding and extreme winds. Like in Kerala, actually during the Kerala flood, during the month it happened in 2018 August. So first 3 days, first, second, and third day of the basically extreme precipitation has been found. It has been observed that it's having the return period of 75 years, 200 years, and the 100 years. So it's basically we can see it's affecting this natural hazard. So what is the role of this hydrological modeling? So what is the role of hydrological modeling in these natural disasters? So definitely we'll have to provide some adaptation and coping strategies towards climate change, towards this natural disaster. So in order to that, we'll have to assess the future. In order to that, we'll have to assess the exact water balance, right? So, and in order to calculate, in order to quantify this water balance, we need a tool that we can couple with this climate data, and we can obtain this water balance. So for that, we need a hydrological model. Apart from that, in order to calculate this future impact study, to assess the future impact, we'll have to have this projected climate data. That is basically that we'll have to couple with the hydrological model in order to get the water balance for the future projections. And basically here I would like to, here I will take a moment to discuss this global climate model and regional climate model. These are the basically primary source of projected climate data that basically provides the climate input for the hydrological model in order to project this future water balance. So So these hydrological models basically provide the understanding of this hydrological process, and also it helps to estimate the water budget components, and also provide to generate the scenario with respect to land use and land change. So, and then we can manage the water resources for the mankind. But so the question is, what is a hydrological model? So hydrological model is a mathematical representation of the response of the catchment system to hydrologic events during the time period under consideration. So basically, this hydrological model is it's a very complex, extremely complex, and highly linearly and highly variable in space and time. So what we do, it's a basically form of the mathematical model that basically represent a catchment. So by using this hydrological model, we try to mimic the basically watershed or catchment characteristics by using this input or spatial data. And for a particular set of meteorological data, we basically calculate the response of this catchment. So basically, hydrological model is nothing but we are trying to mimic the catchment, uh, uh, considering the spatial characteristics of the catchment, and then we can calculate the outflow in terms of runoff, evapotranspiration, groundwater, lateral flow, infiltration, and so on. So that could be helpful to basically analyzing and to planning the water resources. So this hydrological process is for a particular basically catchment or for a particular watershed, for a set of precipitation or basically climate conditions. We by using this hydrological model, we can calculate the river flow, we can calculate the infiltration, leakage, groundwater, so all this. So by using this analytical process, not only we can estimate the climate change impact, but also we can provide the facility to control the floods, and we can also design, we can also provide the storm drain design aspect, and the water demand we can calculate. And more than that, we can provide for the future projections some scientific theories and water resources sustainability, and more than anything, health and safety. So just by using this hydrological process, we can basically estimate the water balance component, and we can utilize for the future planning. So there are some geospatial inputs nowadays we are using for the hydrological model. So nowadays we have some satellite and sensor data that we could use for the flood and drought. So now types of model. So hydrological model can be categorized into the black box model, deterministic model, and conceptual model. So as it mentioned that black box model is basically do not consider the basically input and output relationship. It do not consider. It's a basically it is based on the empirical formulas. It is based on the observations. Okay, so it do not basically, like if I'll give you an example. So unit hydrograph, ANN. So these are the basically black box model. That's where it provides the output is a function of just input. So in such a way that it works. And the conceptual model is based on basically it's a basically gray box model. So it's provide the input and output relationship statistically. And the deterministic model, or basically spatial distributed model, can be further divided into lumped model, semi-distributed model, and distributed model. So lumped hydrological model is a basically it consider a single parameter set. It considers a single parameter of set for the whole catchment. So it do not consider the heterogeneity of the parameters, variables. Whereas in distributed hydrological model, this whole model has been divided into grid, and each grid basically consider the set of parameters. based on the heterogeneity of the catchment. And semi-distributed model, basically it's consider and basically accumulate the similar kind of parameters. So it's accumulate a particular and particular set of parameters. It accumulates and merge into the similar basically parameters of set. So here I would like to share a case study which is basically indicate the hydrological modeling under climate change upon Narmada River basin, and it has been published in Water Resources Management. It's one of the peer-reviewed journal. So in this case study, I will show you the hydrological modeling over upon Narmada River basin. So it's a basically location map of upper Narmada River basin, which is this upper Narmada River basin is located in the central part of river, and it is a basically upper part of the Narmada River basin. And this catchment area of this basin is about 32,500 kilometers square, and the main stream and the length of the main stream is about 350 kilometers. So this whole basin we can categorize into two parts based on the physiography. So the upper part is basically this part, upper eastern part. We can see this part basically hilly and mountainous region, and this part is basically forest and plain area. So there are some heterogeneity within this catchment in terms of physiography. So this section, this basically basin we have considered for the hydrological model. And if I'll go through this methodology framework, so this left part basically indicate the setup of hydrological model, whereas this right part basically indicates the setup of climate input, futuristic climate input. Okay. So in this methodology framework, during the setup of the model, what we did, we basically first step is to delineate the watershed by considering this DEM, digital elevation model. Then we have divided into this watershed into sub watershed, and then HRU. Then we need to generate the HRU, which is a hydrological response unit, which is a basically unique combination of land use, land cover, soil map, and slope map, and for a particular climate period. So here, like IMD, Indian Meteorological Data, this is basically observed data we have provided for the model run, and then we perform the calibration and validation to basically set up the model by considering observed discharge. Then this calibrated model we have coupled with this climate model to get this water balance components. And then after getting this water balance, we can basically evaluate the impact of climate change and hazard under this climate change. And based on that, we can propose the adaptation and coping strategies. So these are the framework basically which I have proposed for this study. But before providing this climate data, there is an issue to select the climate models, because there are several climate models, and it's very difficult to particular climate models for a particular reason. So in this study, we have considered 24 climate models, and we compared the basically 6 climatic variables with the observed data. So in these 6 climatic variables, we consider precipitation, air temperature, solar radiation, sea level pressure, zonal speed, meridian, wind speed. So these are the basically 6 climatic variables we have considered for climate evaluation, for the climate ranking. So this is the basically 24 climate models we have output the models we have compared with the reanalysis data. It's basically surrogate data. So we have compared, and we compared by using the basically evaluation parameters using root mean square and skill score. So we have calculated the agreement in terms of RMSE, root mean square, and skill score between these climatic variables from the climate models and the climatic variables of this reanalysis data. And after getting this root mean square and skill score, we applied a multi-criteria analysis. And after applying this multi-criteria analysis, we obtain a total index for a particular climate model. So as we can see, this root mean square and skill score, we have two evaluation parameters over here, and we have conditions like a S index, I index plus I index greater than 1. If both are basically greater than 1, so 1. So the total index will be 1, and it is less than 1, then it could be a -1. If others, then 0. So basically, considering this situation, considering this total index and these 6 climatic variables, the total index value for a particular climate may vary from -6 to +6. So +6 basically indicates the strong agreement between these climate variables obtained from the climate models and the climate variables of the reanalysis data. So the result of this study, this ranking of this study, basically climate models indicate this MHRD showing the strong agreement between with the reanalysis data, and CNRM also having the strong agreement, whereas this MPI, GFDL, and IPSL, these are the basically climate models indicating a decent agreement between these reanalysis data. So in order to reduce the uncertainty between these climate models, what we did, we choose basically 3 climate models for the climate impact study. So in this part, actually, we have considered MHRD 5, CNRM, and MPI. So MHRD 5 basically belongs to the this climate model actually belongs to the University of Tokyo, Japan, and CNRM actually belongs to the Central National de Recherche Meteorology, Meteo, France, and this MPI model belongs to the Germany. So these models basically are considered as a representative climate models for the particular area for this Upper Narmada River basin. And these models have been coupled with this hydrological model, calibrated hydrological model. So in hydrological model, there are some data required in order to mimic this catchment. So we need spatial data in terms of digital elevation model, land use map, and the soil map. And the hydrological material data, we obtain discharge data from the IMD, especially from this various WRIS India, and then weather data. In this weather data, we had temperature, which is having the spatial resolution of 1 degree into 1 degree, and the daily rainfall is having the spatial resolution about 0.5 degree into 0.5 degree from this IMD. And this regional climate data for the future projection that we have basically that we obtained from the ranking. So these are the basically data we use for this hydrological modeling and impact studies. So in this study, basically as a hydrological model, we consider a semi-distributed hydrological model, which is a soil and water assessment tool. And so by using this soil, which is a basically semi-distributed, physical-based semi-distributed model, and it's a very, it's required very nominal, data for the modeling. So this is one of the reasons we have to selecting this model. So there are particular setup, steps or to set up the model. So in order to set up the model first of all, we had to delineate the watershed, and we derived the step basin, and based on that we derived the stream network. And after that, we have to allot this HRU definition, means hydrological response unit definition. In that, as I mentioned before, that HRU is nothing but it's basically unique combination of land use, land cover, a soil map, and slope map. So basically, we'll have to define this HRU, because this HRU, routed this runoff routed through HRU and then go to the sub-basin, then sub-basin to basin. So it goes like this. So that's why it's required to define this HRU. And after that, we'll have to analyze, we'll have to run the model, and we'll have to select the sensitivity parameters. In order to select these parameters, sensitivity parameters, it's required sensitivity analysis. So that basically these are the parameters we consider during the calibration and validation part. So these are the basically steps we'll have to follow to set up the model. So this is a basically delineated watershed that basically contains the stream network, and it is again then divided into 54 sub-basins. And then, as I mentioned before, that's heterogeneity due to physiography heterogeneity. So in this basically sub-basin, this whole basin we divided into 7 zones based on the homogeneous characteristics of the basically catchment. So this multi-site. So as I mentioned that we had to select these 7 regions, 7 zones, in order to calibrate the model, because it's a heterogeneous catchment. So during the during the zoning of this during the zone, during the dividing this zone, we found that the maximum variability, we found that about minimum variability we have found that 0.13%, and the maximum variability we have found that about 3.52% with respect to the observed one, which has been carried out by the Central Water Commission. So we are basically, this zoning is basically very close to the observed one by Central Water Commission. So apart from that, we required some spatial input data to mimic the catchment. In that, we had distal elevation model, slope map, land use, land cover map, and soil map. And after calibration, we got this basically data. We calibrated. This is a Sandia. Actually, it's basically, let me show you. This is a Sandia. This is a basically final output outlet of this catchment. And at the Sandia, we got the calibration parameter NSE as a 0.77 and R square is to 0.76 at the calibration based on the monthly time step. And the validation validation part basically indicate the NSE value is 0.73 and 0.70 NSE and R square respectively. So according to this, so one of the scientists, actually Morius, has already mentioned that if we have NSE value and R square value between 0.6 to 0.75 and 0.6 to 0.8, we can say this hydrological model is performing good if we are calibrating and validating at the monthly time step. Basically, we can see based on this calibration and validation part, we can say this hydrological model setup is basically performing good. So after that, we have received some sensitivity parameters in terms of curve number, base flow, groundwater, and threshold depth, and so on. So these are the basically sensitive parameters which has to be tuned during the calibration, and we found that this count number is the basically most sensitive parameter in the catchment, and this base flow. So, and basically these are the rankings we have performed, and it is basically at the Sandia only. So the calibrated part has been coupled with the has to be or integrated with this weather data and climate data. So we'll have to run this model, this calibrated model for particular climate and weather data. So in this study, we have been we have run this model for the IMD, basically observed data of the historical observed data, which has been carried out for the 1971 to 2000 for the 30 years of the period. So we had one historical weather data. Apart from that, we do consider this MPI, MHRD, and CIVINAR representative basically climate inputs from these climate models that we have obtained from this ranking, and we had to run this model for this baseline period or basically control scenarios. Apart from that, the data obtained from these climate models for this RCP, basically RCP is basically scenarios, representative concentration pathways. So 4.5 and 8.5 will have to run for that. So RCP 4.5 basically representing the moderate emission scenario, whereas this RCP 8.5 is representing the high emission scenario. So we had run this model for these two futuristic scenario of the obtained or derived from these climate models. And this whole scenario we have divided into three climatic periods. So basically early 21st century, mid 21st century, and the late 21st century. So in total, the climatic periods, for the climatic data, we had 22 runs, and for this IMD for the observed, we had one run. So basically, we had to run this SWAT model considering all this climatic period. We had to run for the 23. We had to perform 23 simulations. So in results, we obtained that this climate change scenarios under this RCP, basically moderate emission scenario, the temperature variability indicate that the linear change in the 10 years of moving average indicates that the temperature, the basically annual mean temperature may increase at the rate of 1.39 or basically about, I can say, 1.4 degree per century. So at the end of the day, at the end of the century, because it may increase by 1.4 degree. Whereas this under this RCP 8.5, this climate mean, basically annual mean temperature, it may rise by 3.5 degrees centigrade. So we can see just by this is basically annual mean temperature obtained from the climatic scenarios, which is basically indicating 1.4 and 3.5 under this RCP 4.5 and RCP 8.5 scenarios. So we can see there is a variability and there is an increase in the temperature. Apart from that, the water balance components obtained from this hydrological modeling under climate change scenario, we have compared with this observed one and the baseline or control line scenario from these climate models. We found that this MHRD 5 is basically precipitation of this MHRD 5 is very close to this observed one IMD, and this MPI basically indicating the very close to this ET value is having the minus 4.44% only. And the MHRD again, it's basically it's not good. Actually, we can't say it's good, but it's very as compared to the other climate models, varying about 10% surface discharge close to this IMD. So these are the basically comparison between this IMD from 1971 to 2000 versus this baseline scenarios from climate models. Apart from that, this hydrological average annual of hydrological responses under climate change scenarios we obtained from this hydrological model, and we derived into this green water and blue water terms. So green water terms, basically it's nothing but it's evapotranspiration and soil water, whereas this blue water indicates the water yield and groundwater storage that we can utilize by the human. So basically, we derive this this whole hydrological responses in terms of green water and blue water for this IMD, means basically observed one for the all three representative climate models for baseline as well as for climate scenarios under moderate emission scenario, under high emission scenarios. So we have obtained. So spatial temporal distribution of rainfall of the last century, basically it looks like this. So it indicates this figure actually indicate the mean annual rainfall variability over the basin, and this is basically winter rainfall variability in the last century over the basin. So the hydrological responses in terms of groundwater, green water, and blue water under these 4.5 scenarios indicates this left part actually left figure actually indicates the green water, whereas this right one is indicate the blue water under RCP 4.5 scenarios. So if I do consider this MHRD 5 model for this early 21st century, I can see there is about 5 to 10% variability in terms of green water throughout the basin, whereas for the same model, but in the late basically 21st century, we can see there is a uncertain, or basically we can say it's very uncertain basically variability we can see in this period, during this period. Similarly, for the blue water under this 4.5 or moderate scenario, we can see there is some variability. There is an increase in basically blue water during this basically early 21st century. But if I do consider this MPI late late 21st century, I can find that this variation could be from positive to negative by 5%. Right? So these are basically these figures representing the spatial distribution of the green water and blue water under this RCP 4.5 scenario. If I'll consider this RCP 8.5 scenario, which is basically a high emission scenario, and I found that this green water and blue water distribution, especially in this blue water, I found that we can see there is basically it's showing there will be any decrement or decrease in water availability in terms of for the early 21st century, considering this MHRD 5 and MPI model. So basically, this figure indicates the spatial distribution. It shows the clear picture about the spatial distribution of this green water and blue water under this moderate and high emission scenarios. So if I'll conclude, so we can see in conclusion, I would like to say that these climate models basically projecting high precipitation and extreme events that could be a cause of flood. So it needs, required to assess the risk which may affect the environment and social and socio-economic development. Apart from that, we'll have to consider this hydraulic regime and related climate factors, and we'll have to assess these vulnerable zones basically. Apart from that, we'll have to apply and we'll have to consider the cutting edge technology and methodology to assess these potential effect of climate change. Apart from that, we need to establish basically some case studies which having the linkage between this climate change and current occurrence of drought and floods to certain reasons, so that we will get the clear picture about that. So how it is affecting and how we can propose the coping strategies. So these are the basically some conclusions which I'll provide you. So thank you. So I'm open for the question now.
Thank you, sir, for such an intuitional talk. And sir, now we will go ahead and take some questions.
Yeah.
So, sir, the first question is from Pradeep Samantre. His question is, how to apply for foreign research internship? And sir, can you show some light on how to do this?
So how to apply for a foreign research internship? Okay, so maybe you are talking about the MS, or I'm not sure whether you are talking about this MS or PhD or just summer internship or something like that. I'm not sure about that. But I'll suggest you. I'll suggest you to for the any kind of research internship, you'll have to have very good research proposal, so that so that you can attract to the professor, and you can attract, or maybe and you can apply, or you can apply some for the research grant. So I'll just advise you to try to get into the research, in that particular research what you're looking for. Okay, so it would be, it totally depends upon research proposal. So, and I'll just, it's better to go through the go to the profile of the professors or faculty, and just ask, you can ask to them with your research proposal. So by that way you can contact, and you can get, maybe you can get the research internship, but it totally depends on your research proposal, I'd say.
Thank you, sir. So the next question is from Pradeep again. He's asking, what is the scope of artificial intelligence in hydrological modeling?
Yeah, that's a very good question actually. So actually, as I mentioned that this artificial intelligence, nowadays actually hydrological modeling, most of the people are using this artificial intelligence in our hydrological modeling. But I would say again, I would say it's a black box model. Okay, so it would be maybe it will provide you in terms of hydrological response, if you provide some input, but it's still it's very difficult to analyze, and it's very, because it's limited to a particular catchment volume, right? So it's very difficult to, but people are applying and people are using nowadays actually. But
Thank you, sir.
again, you'll have to consider that it's a black box model. Yeah.
So the next question is from Mihir Panda. His question is, does SWAT have limits to the maximum area of the watershed it can model?
No, Meher, I guess there is no maximum area for this to consider in STAT model, because people are, because as per my limited knowledge, people are considering, for the continent, and, they consider the continent, and they are simulating, the whole continent considering the STAT model. So there is no limitations as such, I guess.
Sir, I believe that we have addressed most of the questions possible in the given time, as we have reached to the end of this session. So I would like to now call upon Samit, and before that, if Professor Subhajit Mondal wants to speak anything, he may.
Okay, Professor Pandey, thank you very much for informative the talk. Okay, I hope our students get some benefit from your talk. Okay, and in near future, I also will ask you to give us an update on your research topic so that our students also can learn from you and also can see how the research is going on worldwide. And also, will ask if you find that some internship is opportunity is there for our student, please let us inform. Okay, so that I can send our student to your college and so that they can see how that which Dubai is, and they can also have a look Dubai and get some knowledge from your research point of view. Thank you.
Thank you, Professor Subhajit. Now, I would like to request Samit to give the vote of thanks.
Hello everyone, myself Samit Patro, second year undergraduate from Department of Civil Engineering. I am one of the organizing members of the event CIVINAR. Let me start by saying how grateful we are towards Professor Brij Kishor Pandey for taking his precious time and effort to deliver this webinar on hydrological modeling and climate change impact. His contribution in the field of water resource engineering is commendable. He proves and demonstrates how engineers can leave their marks in a variety of fields with their innovations. I am sure everything you told us today will be of great use to us someday. I would like to thank Professor Mandal from Department of Civil Engineering of NITR for gracing the event with his presence. And I would also like to thank SAC for giving us this chance and such constant encouragement to do such events, which help us grow and develop. And of course, the webinar would not be complete without its lovely audience. Thus, I would like to thank you all for attending and making it a success. Last but not least, I thank the organizing team for this event who put tireless hours into making this event possible and seeing it through. Thank you all for turning up for the session. We hope all of you are keeping safe and doing well. We will have more such interesting sessions in the upcoming days. So stay tuned. The video links of our previous sessions are provided in the description. You can go through that, and don't forget to subscribe our channel, and also do follow our Instagram and Facebook pages, and kindly check our website sestnitr.tech for more updates. Take care and see you all again next time. Thank you.